Hi everyone, my name is Connor. I participated in Google Summer of Code this past summer, and I'm excited to talk about an effort I was a part of to improve the efficiency and correctness of implicit modules. First, I want to quickly go over modules and some of the challenges that come along with building them. Then I'll touch on and walk through what I've been working on to hopefully help developers overcome those challenges. So in 2013, the idea of modules were added to Clang as a compiler extension. Since then, modules, a different form of modules, but modules nonetheless have been added to the C++ standard. So modules are great, but one of the challenges is they make building software a little bit more complicated. Regardless of whether we're talking about Clang modules or standard C++ modules, now source files need to be compiled in a specific order. A module's interface cannot be accessed by any other translation unit until it has been compiled first. So I do want to note that this presentation is mainly on Clang modules, and I'll touch on standard C++ modules at the end. There's some similarities, but there's also some big differences. So when it comes to building modules and figuring out the correct order to compile translation units, there's two main strategies being used today. There's the implicit method and the explicit method. For the implicit method, essentially, modules are discovered and compiled as they're encountered in translation units during the build process. So for example, we have a project here that starts with tu.cpp, which depends on module A depends on module B, and module B depends on module C. So with the implicit method, the compiler begins building tu.cpp and encounters an import for module A. The compiler then goes to build module A and encounters an import for module B. This continues until the compiler finally reaches the leaf node of the dependency graph, where it finishes building the module, where it becomes available to its predecessor. The explicit method is a bit different. Typically, there's a third-party tool like a build system that provides the dependency graph for the entire project ahead of time, so that source files can be compiled in the correct order without having to rely on any compile time dependency discovery. So one of the great things about modules is the reusability. You can compile a module once and reuse it across multiple translation units. But because a change in command line can meaningfully change a module's semantics, it's important that the compiler be smart about which modules it's importing. It does that a little bit differently, whether it's following the implicit method or the explicit method. For the implicit method, it looks at a subset of the compiler invocation, and for the explicit method, it looks at the canonical arguments to build the module. So there's a couple issues that come about with the current implementation. For one, like I mentioned, with the implicit method, the context hash is incomplete. There's a couple of things missing, but one of the big ones is search paths, like -i arguments. This is done for performance reasons, as during the discovery portion, there's no scanning phase. And it can be hard for the compiler to determine which arguments are actually meaningful. So instead of including all the arguments and essentially having to rebuild the module every time it's imported, it focuses on a subset. This makes performance somewhat reasonable, but can sometimes lead to incorrect builds. So for example here, we have tu.cpp, which is dependent on the Clang module vector utils. Now, vector utils can either be built with ARM's optimized functions or x86 optimized functions. And we also have two command lines. So the build system will go ahead and execute the first command line labeled tu-arm, and it kind of proceeds as you'd expect. The compiler begins to build tu.cpp and encounters an import for vector utils. So it goes to build vector utils with the ARM optimized functions. Once that's done, the module vector utils is saved to the cache, and tu.cpp finishes building. Now the build system goes and executes the second command line labeled tu x86. It begins in a very similar way. The compiler begins to build tu.cpp and encounters an import for vector utils. It goes to calculate the context hash of the required module that it wants to import. And because the search paths aren't included in that context hash, the context hash for the required module actually matches the context hash for the cached module, the cached version of vector utils that was just built with ARM utils. So instead of rebuilding vector utils with x86 utils, the compiler will just reuse the already cached module. It imports that into tu.cpp and finishes building tu.cpp. So when the user would expect the command line to produce tu.o with x86 optimized functions, in reality, it still has ARM functions. Now, another big issue is the implicit method is a little bit inefficient. When translation units are compiled in parallel, and oftentimes the Clang invocations will encounter an import of a module around the same time, of the same module at the same time. In that case, if that module has not already been cached, it'll be one Clang invocation will just sit idle, waiting around doing nothing, while the other builds the required module, when in reality, there is work that could happen. So for instance here, source 1 and source 2 both depend on module A, but source 2 also depends on module B. Source 2, if the compiler invocation encounters the import for module A around the same time, source 2 will sit idle while the compiler invocation for source 1 builds module A, when really source 2 could go on and build module B. This is actually a lot more common than you might think, as often source files for the same target have a lot of the same imports in mainly the same order. So it's really not that rare to have a few Clang invocations sitting idle, not really taking up time. So both those two issues I just discussed could be resolved with the explicit system, but then you become reliant on a build system. And that's not inherently problematic. There's a lot of advantages with integrating with a build system, but it's a bit less than ideal if that's our only option for a couple of reasons. The one big one is that there exist use cases like a debugger where you might not even have access to a build system. Also, it just raises the barrier of entry for anyone that wants to use modules explicitly. For instance, every time someone wants to take advantage of this functionality, they have to integrate with a build system or somehow provide the dependency information for the entire project ahead of time. This is just a little bit less than ideal, especially if we want to make sure that modules are easy to access. And then lastly, it's a big ask to ask all build systems to support Clang modules and standard C++ modules, especially when that might include supporting dynamic tasks. So we're kind of at this crossing roads where we can have correct and efficient builds, but then we're reliant on this third-party system. So what I've been working on is trying to find a sweet spot where we can have correct and efficient builds and still be independent of a build system. And that's when I introduced the module build daemon. So the module build daemon, from a high-level perspective, is a background process that runs. Clang invocations can connect to the daemon, and share their command line with the daemon. The daemon then takes their command line, scans the translation units for any module dependencies, stores that information in a global dependency graph, and then is free to use that thread to build dependencies as it sees fit. Now, how do we access this functionality? It's as simple as adding a single argument to the command line, fmodule build daemon. That argument will be forwarded from the driver to the front end. The driver never communicates with the daemon. And in CC1 main, right before execute compiler invocation, the front end will connect and share its command line with the daemon. So here's kind of a breakdown visualization of that. The argument is passed from the driver to the Clang invocation, which calls get module build daemon, which returns a file descriptor that the Clang invocation can use to communicate with the daemon. So here's a little bit more details on how the get module build daemon function works. So Clang invocations and the daemon communicate with each other over Unix sockets. So a lot of the mechanisms of determining whether a daemon is there is whether the Clang invocation can connect to the daemon socket address. So it first tries to connect. If that's successful, great, a daemon exists, and it returns the file descriptor. If there is an error, then it uses execute no wait to spawn the daemon, and then periodically checks by trying to connect to the daemon socket address if the daemon has finished initialized. This continues until either a timeout is reached or a successful connection is made. Now, execute no wait takes a command line. This is what the command line looks like for the daemon. As you can see, it is integrated into the Clang binary as a CC1 tool. This has a lot of great advantages because the daemon is dependent on having the same dependency scanner and CC1 argument parsing as the Clang the Clang invocation. So it just helps resolve a lot of the compatibility issues. Once that daemon is spawned, or once that command line is executed, there's 4 main steps that get carried out. First, an instance of the module build daemon server is initialized, and then it forks the process, creates and binds the daemon socket, and then starts listening for clients. Another thing we do to help make sure that daemons and Clang invocations are talking to the compatible versions is incorporate the hash of the Clang version, which includes the git hash of the last commit, into the socket address. So as you can see, base path is underneath the temp directory and includes the Blake3 hash of the Clang full version baked into it. This is where we create the module build daemon socket and where we redirect stood out and stood error. So after get module build daemon has returned a file descriptor to the Clang invocation, it executes a handshake with the daemon. This is mainly to help with the daemon shutdown process and make sure that all goes smoothly. So for example, if for whatever reason the daemon begins to shut down, it can tell any Clang invocations trying to make a connection that it will be unavailable. And if it still wants to connect, that it should spawn its own daemon. We do that using the LLVM library, YAML.io. Great library, fantastic. And what it allows you to do is to translate structs into YAML documents. So how we use it for this project is we define the message protocol as structs and convert those into strings, which get written as a bit stream out to the Unix socket file descriptor. So this is an example of the handshake message. The handshake message contains an action type and a status type. And as you can see, we initialize an instance of the handshake message, use YAML.io to convert that into a string, which then gets written out to the socket. Once the handshake has successfully executed and the daemon has told the Clang invocation that it's ready to do some work, we execute a satisfy dependency request. And this is kind of where the bulk of the work happens. So the first thing that the daemon does is begin processing the command line by scanning the translation unit with get translation unit dependencies. This returns a translation unit dep object, which stores all of the direct and transitive dependencies for a translation unit. And then we take that information for each new module ID, store that in the global dependency graph. After the scanning has been completed and all that information has been stored in the dependency graph, that thread then becomes available to help build modular dependencies. In practice, this global dependency graph is a hash map. So where the key is the module ID, and then the value is all the information required to build the module. So what we do is we just pretty simply recursively iterate through the dependency graph, and then once we reach a leaf node, execute and wait to build the module. Once all of the modules have been built for a particular translation unit, we grab the explicit command line from the scanner, which specifically, instead of just saying build this translation unit, has defined paths to where all of the modules, all the pre-built modules exist. From there, that explicit command line gets sent back to the Clang invocation, and the execute compiler invocation that I mentioned at the beginning gets executed with this new command line. And then I also want to note that essentially what we're doing is adopting the Clang invocations thread for the module build daemon. We're still able to abide by any -j limit set by the user or the system. So there's a lot of work that's been done, but there's still a lot of work remaining. One of the top priorities is just to finish upstreaming some of the existing patches. Those are the GitHub pull request numbers for what's been posted. And then one of the big things we want to do is support incremental builds, which includes just being a bit smarter about how we're managing the cache, and then also saving the dependency graph so that the next daemon or the next time you want to build the project, that can be picked up and some of the work can be saved. Also, we want to improve portability. Right now, the patches on GitHub are specific to POSIX compliant systems. So we want to support Windows and any other platforms that are out there. And then also improve concurrency. And then this is where I mentioned I was going to mention standard C++ modules. There's this big assumption with Clang modules where the command line is just kind of pulled from its predecessor. But that assumption doesn't exist for standard C++ modules. And there's currently no defined way to figure out what argument should be used to build the command line. So that information will come from outside the build daemon, and we're happy to support whatever the tooling study group decides should be the standard. So here are some of the links that I found helpful while working on this project. The top one is the RFC, which I think is a great place for just general discussion if anyone has any comments. And then we have the current pull request, and then a complete draft, which includes what's under review in the current pull request, and then all remaining work, including the building of the modules. And then CMake just announced that their support for C++ standard modules were going to be non-experimental. So I included that, and then some other interesting talks and explanations if anyone is curious to do more reading. So that's pretty much it. I'm happy to take any questions.
Hi, thanks for the talk. Obviously, I don't actually have any experience with modules myself. I just have a rough estimate of how this works. So I just have one question. If the build system is not aware of this functionality, how can it provide an optimal order of compilation units sent to the Clang command line? Or is this pretty much not a requirement? It just generates maybe suboptimal sub-dependency graphs, and it's acceptable in this state.
Yeah, so I think that our goal with the module build daemon is to use it in cases where you don't have access to a build system. If you've got, for example, CMake set up with support for C++ 20 modules, then you might as well go ahead and use that. But for example, Clang modules and the other instances I mentioned where you might not have access to a build system, that's where this really comes into play. And the daemon itself kind of acts as a build system. Because of the global dependency graph, essentially gives Clang invocations a way to communicate with one another and just share more information.
Thanks. Thank you.
No problem.
Hi, thanks for the talk and the work. I have a question. If you have two builds are done at the same time, will they share the same build daemon?
So potentially they could. It's really important that that daemons and Clang invocations come from the same version of Clang, but you could definitely work it so that the daemon builds multiple projects at the same time.
Yeah, I mean, by default, you use hash like your name of a socket is using like a Clang version and path and stuff. So as long as you use the same Clang, they'll just by default use the same build daemon, right?
Yes, that's correct.
Okay, I guess it's not an issue. But like another question is, in an implicit system, if a module A is built with different flag than the module B that uses module A, how do you resolve it? Like this, you have old make files and you just say, yeah, when I build the library, I need this argument. But when I build thing that uses a library, I don't need this argument.
Could you repeat the question?
So let's say you have two modules, module A and module B that uses module A. And when you build module A, you have extra argument, which you don't pass when you build module B.
So I'll need to confirm to make sure I have this right. But for the implicit method, when you go to build like the translation unit, it'll go to build module A with the command lines of tu.cpp, and then it'll check to see the context hashes for module B, and if they don't match, it'll build a new module B with the right command lines. Now, if you know the difference in command lines is one of the things ignored by the context hash, then it'll include that and it'll just be a broken build.
Okay, yeah, sure. Thank you.
It looks like the thing you described is all running on locally. How does that work with like distributed compiler service?
Yeah, that's a great question. And to be completely honest, distributed builds is a little bit further down the roadmap, and I haven't been able to give it a deep thought.
Okay, thank you.
Hi, I think this is pretty cool. Thanks for working on this.
Of course.
Is there any plan to replace the implicit modules mechanism with this mechanism at some point?
Yeah, no, that's a good question. That's one of the first things I was wondering when I started working on it. And yeah, there's some complicated things that go on with building implicit modules, and I think the idea is to replace that with this.
Thanks.
Hey, first of all, you did all this in the summer, right? Wow. Right, and quick question. So how does the daemon know when it can shut down?
So
Is it like timer?
yeah, that's a good question. So the plan is to kind of just have the daemon time out eventually. So if it doesn't receive any new Clang invocations after a certain point, it'll just shut down.
Ah, nice.
Thank you.
Are there any more questions? I guess then let's thank Connor.
Thank you.